Hello, in this video I'm going to be talking about how the approximation, how we can approximate the binomial distribution with the normal distribution. Now, there's actually the way this is covered often at A level is it's just done in a mechanical way and how to do the questions. Things have changed a little bit recently because the calculator has made many of what would have been the questions in the old days redundant because a calculator can work out any norm in any binomial distribution. But I think it's interesting from a theoretical point of view anyway, because there's more going on than meets the eye. So in this video I'm going to take a little bit of a more theoretical view of what's going on here, also a little bit of a visual demo, and we will do one example which is taken from the edXL, the actual new edXL textbook, which still makes quite a thing of binomial distribution with normal distribution. I have a sense that these questions are going to become less common because there's less of a point to them, but it's still there and it's still on the course, so we need to cover it. And I'd like to, as I say, perhaps take a deeper look into this than is absolutely required at A level. I'm going to mention a couple of things that many of the students who look at this, many A-level students, won't have seen, and actually are not strictly required. I'm going to talk about something called the Bernoulli distribution. First of all, bear with me. And then also, and further math students will go on to do this, if I haven't done so already, talk about the central limit theorem and how that applies to how this is actually relevant in this context, and what's to try and make a deeper look of what's actually going on. Okay, so the Bernoulli distribution, let's rub that bit out for the time being. Let's call it the distribution such that y, and basically let's write it as in a table, basically 0, 1, and it's got half and half. Kind of boring distribution in a way. Let's call it y probability y equals to y. It's kind of like a binomial, well, it isn't kind of like, it's like a binomial distribution with one trial, basically. That's what it is. It's a special case of binomial with one trial and probability. Actually, it doesn't have to have probability a half. It could have probability p and 1 minus p. So that's probably p and 1 minus p. P is a probability of excess and 1 minus p is a probability of it not occurring. So that's a binomial distribution. Now the binomial basically is a binomial with n trials, probability p is basically a combination of n lots of this. So if we do this n times, if we kind of like take n samples of this distribution and call it x, say, x equals y1, y2, y3, y4 up to yn, okay, so where y1 is this, where y1 up to yn have Bernoulli distribution, then basically, if you think about it, this is going to be the binomial, because so for example, imagine if all of them produce the number 1, then we're going to have a total of n, which would be the n in our binomial. So we could then write our x, probability x equals to x, if they were all, so I'm struggling drawing a straight line at the moment. if they were all, producing, all n things produced that, then there would be n here, and we'd have a particular probability. But of course, we could have all having 0, 1, 2, 3, and of course, the ones in the middle are going to be more likely. This one at the end here would have to be, because we would have had to have p n times, and this one here would have had to have, we'd have had to have 1 n times, and here we'd have to have 0 n times, and so on. So basically, the binomial distribution can be thought of as the combination of n equivalent Bernoulli distributions. So why have I mentioned this? Well, by the central limit theorem, and we will come, for further maths students, we'll come on and study this, says that if you, well, it actually says it in a slightly different way, but it's related, that if n is sufficiently large, if we take, n 100 or 1,000 or whatever, then the distribution, if n is large, the distribution approximates to normal distribution. Okay, so I just wanted to, so that's what's going on here. It is actually, there is some pure maths going on behind this. It's not just a coincidence, nothing else. Things are not normally, are they? So it's not just by chance that this occurs. The binomial often can be thought of as a kind of discrete equivalent of normal distribution if binomial is, if the value of n is large. However, there is a caveat here. I'm going to give you a visual demonstration of this as well now. I'm using GeoGebra here. I should say that this is not my animation here. I just googled GeoGebra normal binomial approximation, and this is what's come up. So thank you for, I would like to say the name, but thank you for whoever actually come up with this. It saved me some time, and I say it's a good tip for you actually. If you ever want to see an animation and you Google it, you'll find plenty of things, and GeoGebra in particular has quite a few inbuilt animations that you can see, and some of them are web-based or app-based or whatever. Right, now let's just talk about the maths for a little bit. The red curve is the normal distribution for the equivalent binomial, and we can convert from one to the other by just making sure that the mean and standard deviation are the same for the two distributions, and we know how to work out the mean of a binomial distribution, and we just make sure that the normal distribution has that same mean and that same standard deviation. I should also say, of course, one thing that's really essential that we get here is that with the normal distribution, it's the area underneath, whereas with the binomial, it's actually the height of the bar. And deliberately, we've not put gaps in bars in this time. Often we often kind of like to put gaps or do represent the binomial with a kind of stick graph, but it doesn't really work here when we're trying to kind of compare the normal and the discrete. So with the blue one, it's really the height of the bar that matters, whereas with the normal distribution, it's the area. But what's interesting here is that they're almost the same, because if the actual length is 1, which it will be, if the actual kind of width of the bar is 1, then the height of the thing will be the same, will be very similar to the area, but not exactly the same, because we can see that the area under the curve isn't exactly the same as the area of the bar. Okay, now here the sample is only 34, and it's still not looking too bad. And here is even down to 20. It doesn't look too bad. A little bit more inaccuracy around it, obviously, but it's still not looking too bad. Yeah, thinking about this thing about the area and the height being similar, some of you may recall, if you looked at my video on the normal distribution, absolutely very kind of emphatically telling people not to use PD, normal PD, and I often had protests from students saying it works. Well, this is a kind of reason why it might work. If the number of possibilities is large, and you're doing it, and it's a kind of situation where the height of the bar would be the same as the area underneath it with width 1, then it will give an approximation. But never do that. Never use normal PD. But there's a connection there as to why the normal PD function on your calculator works, but you should never ever use it. Probably most of you don't know what I'm talking about there, but it doesn't really matter. But anyway, let's get on with this. So basically, if I make P kind of close to the end here, let's try and move it down a bit. Yeah, it doesn't actually work because it's if I make P, it actually becomes worse and worse here. And if I make P equal to 0.5, let's make the sample size a bit bigger, 50. There you go. It's becoming a little bit more jagged, and you can see around here it's becoming a little bit dodgy. Okay, so basically for it to, it can actually, for surprisingly small values of n, if P is close to 0.5, don't have to be that close to 0.5, but if P is exactly 0.5, say, or very around it, the actual let's take that down. The actual similarity between these two is quite a lot, even for relatively small values of n. Whereas if P is a little bit more further away, we might need a bigger sample size, say here, but it's not bad, even with P is equal to 0.8, say, and n is 60. It's not doing too bad a job. It's getting a little bit more accurate around the n values here, but it's not been doing too bad a job, even with P being quite a long way from from 0.5. And as I've just said, because of the central limit theorem, eventually, if we made n 600, say, even with P being close to the even quite not close to 0.5, quite a long way away, this approximation can be pretty close. Okay, so hopefully that has been useful, but I'll go back to the actual main text. Okay, so this means normal distribution can be used for to approximate binomial distribution provided n is sufficiently large. Right, so basically, even if P is, but so how large depends on the value of P. The closer P is to 0.5, the smaller n needs to be. Okay, so the closer and e.g. n equals 20, P equals to 0.5 is good. And what you will see, I don't really want to become too rigid on this, but you will see some people say, or some statisticians, or you might see in other videos, referring to the value of NP. Okay, you will see, and people say different things. Some people say NP needs to be, some people say NP greater than 10 or greater than or equal to 10. Others say NP greater than or equal to 5. Okay, whatever. But basically, if n is sufficiently large, eventually it will approximate to a normal distribution, even if p is really, close to 0 or close to 1. So basically, just to summarize, because I've probably waffled on a bit, n large, p close to 0.5, but hopefully you can see it doesn't have to be that large if p is close to 0.5. So those are the kind of two criteria, and some people refer to the value of NP as an absolute thing. People like rules, don't they? NP greater than 10, good. NP less than 10, no good. I don't look at it that way. It's a kind of sliding scale. It gets better as n is large, and the larger n is, the better it gets, and the closer p is to 0.5, the better it gets. But I suppose the one thing I would say is, with p close to 0.5 doesn't mean you can have small n. It needs to be at least about, I would say, 10, it's got to be over 10 even with p is 0.5. Okay, so hopefully that gives you the gist. Now, the one thing, I'm going to do a question in a moment, but the one thing we need to bear in mind is that the mean of binomial, if we have a binomial with n trials and p, we can say the mean is equal to np. So, and the standard deviation is equal to np1 minus p. So that's the variance. The standard deviation squared, the variance, is equal to np n minus p. So that means that, so I'm trying to make space here, that means that can be approximate the equivalent normal approximation would be, let's call it, would be normal and mean NP and standard deviation NP1 minus P squared. Don't forget that's the standard deviation. You might write it like that. So the variance is equal to that. So that is how the approximation works. So if you're given a binomial, you need to work out the mean and the variance and the standard deviation of it, and then you can work with the equivalent normal if you're doing it that way. Okay, right. So the other thing, and in the previous video, I talked about the continuity correction. So a continuity correction must be applied. We always apply a continuity correction when a discrete distribution is being approximated to a continuous distribution, in this case the normal distribution. Okay, so let's do an example. As I say, for A-level students, especially of OCR, I'm not sure how likely this kind of question is now, but it is possible, and besides we need to understand the principles here, and it's good to talk about continuity corrections and things because it's a kind of important aspect of the course. So here we go. For a particular type of flower bulb, 55% will produce yellow flowers. A random sample of 18 bulbs is planted. Calculate the percentage error incurred when using a normal approximation to estimate the probability that there are exactly 50 yellow flowers. Okay, so let X be binomial, and we've got 80 trials, and the probability that they come up with yellow is 0.55. Okay, So let's work out what the probability of x is equal to 50 just from the binomial. So probability x equals 50. Now, I do find students who are used to using the probability kind of facility on the calculator go straight to their calculators here, because using your calculator you will find that binomial and probability PD will work and it'll give you the answer. But I don't think we should forget the formula for this. The formula being the n minus r for nr formula. So we've got 80 C50 times, and we need to have 50 successes, if you like, 50 successes times by if we've got 50 successes, in other words they're yellow, then we have 30 that are not yellow, and the probability of that is 0.45. So basically you've got this many possibilities, 80 C50, quite a lot of them basically, and the probability of each individual one of them is 0.55 to the power of 50, because the probability of getting a yellow one is 0.55, and it happens 50 times, and the probability of not getting a yellow is 0.45, and that happens 30 times, and there's 80 C50 different ways of getting that. Okay, I could have used a calculator, but I just can't help the temptation to put that in to just go to first principles, because we should never forget that formula really. So now we're going to use the normal now we're going to use normal approximation, because it's reasonable, because n is really large, p is close to 0.55. If you to multiply the two together, you get something over 40. So it's definitely going to be pretty it's going to pass our kind of criteria for normal approximation to be used. Right, so yeah, so what we're going to do is say what the mean is NP. So the mean is equal to 80 times 0.55. Okay, and that equals to 44. Okay, and the standard deviation squared, or the variance, is equal to 80 times p, which is 0.55, times 1 minus p, which is 0.45. So so that's equal to 19.8. Remember, that's the variance, not the standard deviation. Okay, so what I'm going to do is call this something different, because it's a different distribution. Let y be normal distribution with mean 44 and mean 44 and standard deviation 19.8. Sometimes even like to write it like that to emphasize the standard deviation is 19.8, square root of 19.8, and the variance is 19.8. Okay, so we're not using the tables anymore. So what I'd like to do is say, right, we want to find a probability that x is equal to 50 equals to, now in the previous video I kind of said use CC to show that you're using a continuity correction. We don't really need to here, because I've defined this using y, so I don't have to write CC. You can if you want, but I don't have to. The probability that y lies between 49.5 and 50. And I can put a strict or inclusive inequality there, it makes no difference. 50.5. Basically, you've got the value here, it could go either side. you've got the value 50 here, and we go 0.5, and if we have 51 there and 49 there, we go 0.5 either side to allow for this thing called the continuity correction, because we're now dealing with the continuous distribution. Okay, so now we can just go straight to the calculator to actually work that out, and then we can work out our percentage error. Okay, let's do that then. Right, so here we go. So menu 7, and we've got we're dealing normal CD. So normal CD, that's 3. Oh no, menu, I got it wrong. Menu 7, we've got normal CD, which is 2. The lower value we want is 49.5. The upper value we want is 50.5. The standard deviation, be careful, not the variance, so that's the square root of 19.8. And the mean, which is equal to 44. Okay, and that comes to 0.0362 to 4 decimal places, or to 0.0362. Now it's obviously, even though it's okay to write those numbers and round them in your working, I would be, because we're talking about percentage error here, I'd be storing this number on the calculator or writing out more significant figures than we've written down there. Use the store on your calculator, because when you're finding the difference between those two, any small inaccuracies are going to be quite pronounced. So I'm going to be using that. Memory function on my calculator, but I'm not going to bring it up on this occasion. I feel like I need to get to an end of this video because it's gone on a little bit. Okay, so percentage error equals 2, and we want to find the difference between these two. So let's just, we don't want it to be negative because we're not interested in whether it's bigger or smaller. So just take the smaller one from the bigger one, divide by the actual one. Wouldn't make that much difference here, but it might make 1 decimal place difference. 0.0365 times by 100, and that gives us a percentage error of 0.82%. Okay, so that's the percentages. So there we go. That's how likely a question is like that. I don't know. It is kind of perhaps more realistic because they've kind of got us to use both things and to compare them. It's quite a small error with n being large, and with n being so large and p being relatively small to p being relatively close to 0.5. Okay, I hope you found this video useful. Okay, important things here were just the main principles and the this idea of a continuity correction. Okay, so that's important. Okay, bye.